So I guess I'll start the recording. To a quick announcement about the homework. I also sent out email, I think on Monday. Right? So it'll be due on the 27th, which is Wednesday, instead of the 29th, which is a Friday, because on the 29th we have our second exam, and this way I can post the homework solution on Wednesday for you guys to look at it. Okay. So other than that, let's start the lecture 18. Right. And today we're going to look more about random walks, and we're going to prove the Stirling's formula. Right. Simple random walks and Stirling's formula. Okay. So now let us quickly recall what we have done just last lectures, right? So last lecture we proved we proved the equivalence for the definitions of a state being recurrent, right? Just definition, or just recall. I'll just recall. Right. So X inside our state S is recurrent. If it satisfies any one of the following. One. Right. And it's because we proved we proved on Monday that these three statements are actually equivalent, right? So the probability that Xn visits X. Okay, I'll just write Xn is equal to X for infinitely many n. Right, given that X0 is equal to X, this probability is 1. And the second statement is the probability of the heading time to the state S is finite, almost surely, given that we start at our X. This is also equal to 1. And the third condition is as a summation, right? So we have a summation, n goes from 1 to infinity. We look at the n-step transition probability from X to X. The sum being infinite, right? So we proved these. And out of these, we use number 3. So previously, we used number 3 to show that if two states, they communicate with each other, one of them is recurrent, then the other must also be recurrent. And if one of them is transient, the other also has to be transient, right? And on Monday, we also using number 3, we proved that the random walk in 2 dimensions, when p is a half, the chain is going to be recurrent, and when p is not 1/2, the chain is transient, right? For random walk, simple random walk on Z. So we see that if p is a half, then the entire chain. But what we proved is then we just say that the origin, then 0 is recurrent. Right? And of course, because the entire chain is irreducible, so the entire chain also implies every other state inside or any other integer is also recurrent, right? Because they all communicate with each other. That's in the same communication class. And also we have shown that if p, well, we didn't show this, it's part of the homework. If p is not a half, then 0 is transient. And of course, then this also holds for any other integer. Okay, I'll just remark and replace 0 with any integer. And the statement still holds. Right, so we can replace this 0 here with any other integer, and the statement still holds. And a minor remark is that I think last time when we did the Stirling's formula, we almost thought this as an equality. This is okay, just to avoid some of the minor analysis steps. Right? You'll see also in the homework. And today we'll be looking at a proof of the Stirling's formula. So you can imagine in our homework 3. I also just wrote it in the homework statement. Just assume like n factorial is equal, which is not true, of course, square root of 2 pi n, and n to the n, e to the negative n. Right. So just assume this. Yeah. So it's totally fine. And I think I include the precise statement about this. Okay. I don't know if I should say more. Sure. Okay, I'll just stop here. Okay. Yeah, maybe I'll say more during the second half of the course when we actually proving the Stirling's formula. Okay. So today, okay. So maybe I'll also just mention this. 3. Okay, sure. Okay, so today, let's skip Z2. Let's go directly to Z3, and I'll just say what happens in Z2. Today we look at just simple random walk on Z3 in 3 dimensions. And of course, in this case, we're going to look at the more interesting case, which is the walk essentially is it's symmetric, right? So in Z3, there are 6 directions for each vertex to go, right? So imagine that in Z3 that we have, so this is 1, 2, up and down, 3, 4, and also this direction, right? So there, for each vertex here, it can go to 6 different directions. You can think about it, it's like positive x, negative x, positive y, negative y, and positive z and negative z, right? So there are 6 directions for steps, right? So there are 6 directions. Okay. And now, naturally, then we just define the transition probability in this way. So we'll just look at the pxy. It's just going to be equal to 1/6. If x and y, they're adjacent, right? You can, or maybe more precisely, I should say, if the L1 norm of x and y is 1 and it's 0 otherwise. And this just means that between the point x and y, there's just a single edge, a unit edge between them, right? So you can imagine that this point here is the x, and then there are other possible points, which are these 6 points inside Z3, right? And then it takes a uniform, with uniform probability, the chain will pick one of these 6 directions and then just go there. So it kind of corresponds to the case when P is a half, right? In Z1, we either go to the left or right with probably half, and in Z3, we will either go to, forward, backward, left or right, up and down with probably 1/6. That's all. Okay. And then something it's a little bit special here is, well, not really special. So the goal here, where we're going, is that we're going to show that in this case, then the origin here is no longer going to be recurrent. The origin becomes transient in this case. Okay, that's good. Camera. Let's draw the line. Okay, so maybe I'll write go. We will show that in this case, the origin, I'll just write 0, 0, 0. And sometimes I'll just write a single 0 when it's clear. 0 inside our state space Z3 is transient. Yep. And again, the approach is before, and to do this, right? To do this, we show that the summation as n goes from 1 to infinity of Pn. So over here, I'll just write 0 and 0 instead of the triple zeros. This is finite. Right, so this is going to be the way we do it. Okay, so now this is something that, as we have seen before, so in order for the chain to return back to 0, the number of steps just has to be even, right? Because if you take all number of steps, you can never just return it to a cell, right? Just like before. So again, note that Pn of 0, 0 is 0 if n is odd. Right? So there's no way for you to return to itself when you're odd. So, and then we just, again, then we just look at, right, so we have the summation, n goes from 1 to infinity, p of 2n of 0, 0. Okay. So maybe, and I guess another remark is the following. So this is, you can think of this as one. Another observation is that, let's see. Okay. Okay, I'll just move this up a little bit. Okay. So if the Markov chain, or the random walk, I should say, it doesn't matter, returns 0, return to 0 in 2n steps, then we must have the following. So I'll just write down the equation and I'll define these variables. Then we have I, I'll write right here, then I is plus j plus k has to be equal to n. Then now I'll define what ijk is, where I, j, k are the number of steps okay, I'll just mark the 3 directions as E1, E2, E3. You can also do it with X, Y, Z. E1, E2, and E3 directions. Right? So now there are total 6 directions, right? Because for E1, there's a positive event, negative E1. For E2 direction, there's a positive E2, negative E3, and then E3 directions. Right? So, I mean, a way you can think about the second remark is that, well, since we're going back to 0, so the total number of steps that we take in the E1 direction has to match with the total number of steps we take in the negative direction, or else the chain won't go back to 0. And then so we just only have to look at the positive directions. And then if we know it returns in 2n steps, then for the direction that is going into the positive E1, E2, E3, they just have to add up to n. And then we'll need the other n steps for it to return, which means we'll take like the negative I number of negative, sorry, E1, I number of negative E1, J on negative E2, and K of negative E3. Okay. So now this allows to rewrite the following. Rewrite this. Now we just look at a single probability. So P2n of 0 and 0. Okay. So we can write this at the summation of I, j, k is greater than 0, and then we condition on I plus j plus k is equal to n. Right, so these are all the possible combination of steps that we can have. And then, of course, now we just have to compute the probability. Then, well, for each particular path, the probability will just be 1 over 6 to the 2n. And then the number of paths for each configuration ijk will just give me by 2n. And then choose ijk. Okay, maybe I'll just write out the factorial explicitly. Maybe it's more clear instead of doing this like multinomial thing. So I'll just write on the top we have 2n factorial, and then we have I factorial, j factorial, and k factorial square, right? So if you're familiar with like multinomial, it's like 2n, choose ijk. Right? So these are all the possible possible combinations of ijk, and this counts like for fixed ij and k. What is the number of ways that you can order the steps to get distinct path? And that adds 1/6 to 2, and this is the probability of getting for each particular path. Right? So when you add them together, this gives us the probability that we go from 0 to 0 in 2 in steps. Okay. Maybe I'll take a pause here. Any questions? All right. Okay. So next, let's rewrite this term a little bit. So same thing, ijk, Archer ijk, and I plus j plus k is equal to n. And okay. In this case, right in this way, so we have 2n factorial, and that's divided by n factorial, and on the top, I'll add n factorial, and on the bottom, I have I factorial, j factorial, k factorial. And then I just have 1/6 to the 2n. So I just add, multiply and divide the same term. And then I'll bring this term inside because it's independent of ijk. And from here, 1/6, I'll bring out a half. So I have 2n, choose n. This is coming from this term. Okay. And then we have the summation. Okay, sorry, I think from the notes. Let me also bring out something else. From the 1/6, let me bring 1/2 to the 2n. And then we have the summation ijk, where I plus j plus k add up to n, and then we just have the other remaining terms inside. So in this case here, okay, this would just be n factorial squared, and then the same thing as I factorial, j factorial, and k factorial squared. Okay. And I have 1/3. Right. Okay. So from here, we're going to break the integer n into 2 cases. And then essentially, a lot of analysis will cover by the first case. Right, so in the first case, we assume that if n is a multiple of 3, which is when n is 3m. Right, so this is the integer n. So this is i.e. a multiple 3. Then we have the following inequality. So I'll write down the inequality, then I'll try to give a quick justification. So imagine that we have, so I'll just write n factorial over I factorial, j factorial, and k factorial. This thing is less than or equal to just 3m factorial of m factorial, and m factorial, right? So where n here is 3m. And as we will show, then as we will show next. Okay, so maybe I'll just say a little bit about this inequality here. So essentially, it says like, so it's only one I, j, and k, they're all equal, that it kind of takes the maximum value, or else like by changing these value I, j, and k here, it will decrease. Right, so that's just and a quick argument that we can argument in the following way. So so let's look at okay. Let's just rewrite this term. That's n factorial. Let's say I factorial. Maybe okay. Let me write it differently. So let's do I minus 1 factorial. J plus 1 factorial and k factorial. And I'll explain the plus minus 1 plus 1. I mean, the reason I do a plus minus 1 here and plus 1 here is to make sure that the sum of these three numbers here still add up to n, right? So because that's like one of our restrictions for the ij and k, right? And it only makes sense. It's a like multinomial distribution if the sum of these three is n. So in this case here, I just decrease I and increase j, so they still sum up to n. Right? So this is equal to n factorial of I factorial, j factorial, and k factorial, but with multiply a additional term here, right? So in this case here, I guess we would need a j plus 1 on the bottom. Let's see. Did I do this correctly? Oh yeah, okay, so sorry. I mean I on the top and the j plus 1 on the bottom, right? Maybe I'll take pause here. Right, so this is just algebra for just definition factorial, right? Because the I here will cancel with I factorial to get I minus 1 factorial. J factorial times j plus 1 is j plus 1 factorial. Right, so now let's focus on this term here. Purple. Maybe purple is hard to see. I'll use orange. This is better. So that's right. So a quick observation that we can make is that so this is less than or equal to 1. If I, let's say, is less than or equal to j. I mean, it's actually strictly less than 1, right? Because we have the j plus 1. Okay. Right. So so then this inequality essentially shows that if I is less than or equal to j, then we have the following, right? So we have, well, this thing gets multiplied by something that is strictly less than 1. So we have n factorial over I minus 1 factorial, j plus 1 factorial, and k factorial. And then we have, then this term here will be smaller than or equal to n factorial over I factorial, j factorial, and k factorial. Right? So this is true in general. And the claim is that now this would eventually just implies our inequality. So you can think about it in this way. So over here, if I is already less than j, and subtracting I and adding 1 to j just makes their difference bigger, right? So essentially what this inequality says, just making these indices, making the difference between these indices bigger, the number gets smaller. And so over here, then it's clearly when they're all equal, then they will take the biggest value, right? Because as soon as like if we increase the difference, then the quantity here gets smaller, right? So so if this means if we increase the difference between ij and k, and I'll just say the value gets smaller. The value gets smaller. The value. Okay. So let me take a quick pause here. Any questions? I'll also just highlight this. Right. So essentially, our inequality here just follows from this box. Okay. Let's see. So now let's call this one star. So it's just the last equation here on the board on the previous board. Let's call the star. So continue from there. So now we know that the star here can be upper bounded in the following way. So it's less than or equal to 2n, choose n, and then 1/2 to the n, and then we have the summation of ijk, and I plus j plus k is equal to n. And in this case here, we call that n is still equal to 2m, right? So I'll just write here. So we are also still in the case n is equal to 3m, sorry, not 2m, 3m. And let's just replace this by let's say, okay, so let's do it in this way. So let's over here we have this n factorial divided by I factorial j factorial and k factorial squared. And let's just replace one of them with 3m with m factorial, m factorial, m factorial. And I have 1 over 2 to the n. And then the reason we want to do that is because of this term matches together nicely with this term. So I'll just now, this is 2n over n, 1/2, which is the nth power. And then we have 3m factorial divided by m factorial, m factorial, m factorial. And then we have the summation that ijk, I plus j plus k is equal to n. And then we have n factorial divided by I factorial, j factorial, k factorial, and then 1 over 3 to the n, right? And then the reason why to kind of do this is because this part here, this is just a, this is essentially the multinomial distribution, right? So this is equal to 1. This is because this is a multi distribution. Okay, so it remains just for us to handle this term here. So again, well, this part again is just going to be Stirling's formula. So I won't get into the details. Maybe I'll just write out the other results. It's essentially equivalent to C, and then it's 6 over n raised to the 3/2. And you guys just use, because now every term here is just going to be a bunch of factorials. And then just take the Stirling formula as equality, just plug them in, and a bunch of the terms will cancel. So in the end, we get this. Right? So this finished the case when n is equal to 3m. So the next case we will look at when n is in the remaining form. So, okay, so this is the first case now. So now remaining if n is equal to, let's say, 3m plus 1, or just 3m, or n is equal to 3m plus 2. And the claims that we can just bound it trivially just by the case when n is 3m, right? So this is because now p of in this case is 2n. It's because let's see, how should I write it? Okay, sure, I'll just write it this way. P of okay. Let me just write directly in terms of m. I think it'll be more clear. Okay, p of 6m of 0 and 0. This is going to be bigger than or equal to 1 over 6 squared. And then p of, let's say 6m minus 2. And I guess it probably makes more sense to do, they're equivalent, of course. Let's just do, sorry, let's change the plus sign to a minus sign. Of course, they cover all the choices. Okay. And 0 and 0. And I'll just also write out the next equality, and I'll ask you guys why. 6m of 0, 0, 1 over 6 to the 4th power, 6m minus 4, 0 and 0. So why do we have these two inequalities? Yeah, sure. Sure. Right. So that's the first case we look at, and when n is 3m, we get this estimate, and then the other remaining case is when n is either equal to 3m minus 1 or 3m minus 2. Right. So this covers just all. Yes. I mean, yeah. I will show there are because of these two inequalities. Right? Because essentially it says when n is a multiple of m, there will always be some upper bound for these type of for the other two cases. So over here, maybe I was just asking, why are these two inequalities true? Yeah, sure.
N that is I plus j plus k in the xyz direction.
Sure. Yeah.
Away from the origin, is that right? Is that mean for the second n step, it will be the minus I minus j minus k, then it will not return to the, it will not equal the minus I minus j minus k, that it will not return to the zero.
Well, I guess maybe I should. So this here, I plus j plus k is equal to n. It doesn't mean the first n steps, right? Your Markov chain can go to, let's say, positive 1 and then negative 1, negative 1. Oh, sorry, that's like returning to 0 in 2 steps. Okay, so imagine your Markov chain can doesn't have to take all the positive direction in the first n step. It can take like a mixture of steps, right? So maybe it's in 2 dimensions, I guess it's easier to draw. Okay, I'll just draw on this board and then I'll erase it, right? So okay, so imagine that in Z2, we can just take, like, say, for example, we can take, so these are all in positive direction, and then I can certainly take steps in the negative direction, right? And then we can take negative direction and then more positive direction, right? So we can do something like this. Suppose this is 0, right? It just means that, okay, so it's like if we return the 0 into 2n steps, then the sum of steps in all the positive direction, they just have to be n. That's all. Because you'll need the other n step to come back to go in the negative direction. That's all. Yeah. Yes, yeah. Sure, yeah, this is in 3-dimensional. Yeah. This, sorry, what?
Because this is the case of the 3-dimensional.
Yep.
The two will not come back together. In that case, the other n that is not minus I minus
It will come back to 0, right? I mean, if we suppose the path return back to 0 in 2n steps. So there's no probability here, right? Just think about all the, like, think about it, given any path that you go start from 0 and then come back to 0 in 2n steps. It just has to satisfy this property. So that for n of the steps, it can take in the positive E1, E2 direction. And then for the other n step, it just has to be in the negative 1, negative 2. There's no probability here in this statement. It's just a deterministic statement. It's a property of a path that going from 0 out and then come back in exactly 2n steps. Right. So you can, yeah. So there's no probability here involved. So I mean, yeah. So just like in the picture here. So how many steps? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right. So in this case here, it's a one example of a path that I return to 0 in 14 steps. Then in this case, the number of right steps plus, so in this case, then right steps plus up steps has to be equal to 7. And on the other hand, the left steps and then plus down steps has to be equal to 7. If in total, this is 14 steps. Right, so it's just like this, just observation is completely determined. If you draw any other path that returns 0 in 14 steps, and they will also satisfy this equality. And what do you mean by event over here? So this is nothing probabilistic. It's there's no, so imagine there's no Markov chain involved. You're just drawing a particular path that you start, return to 0 in exactly 2n steps. Right, so and then it just has to satisfy this condition. Yeah, just yeah.
Add the concept of the probability into it, and that to the infinity, it can be 0.
Yeah, the probability will be 0. Yes. Yeah. Right. Okay. So, any other questions? Yeah, before we can clarify. Yes. Oh, yeah. Sorry, I forgot. Yes. Sorry, can you say that again? Oh, yeah, it's 2n. Yes, it's 2n. Thank you. Yeah, it's a typo. So over here it should be like 2n. Yes. And then, okay, I'll just here it's Sterling. Okay, so maybe come back to these two. I mean, essentially, you can think about this as just like a special case of a Kolmogorov like equation equality that we have seen, right? So over here, we're required to return to 0 in 6m steps. And over here, it's the probability that we return to 0 here in 6m minus 2 steps. And then afterward, we just take a particular, let's say we just take a direction, a step in the E1 direction. And then next, we just take from a E1 direct, sorry, I shouldn't say that. Yeah, sure. It's, and then we just take a step from the E1 step, E1 direction back into 0, right? Does that make sense? So, okay. So think about over here is that we return to 0 at exactly the 6m steps. And over here, it's we can already return to 0 at 6m minus 2. So over here, it's something that suppose this 0, of course, it can cross 0. But then we just like after 6m steps, we return back to 0. But then over here, this is just, so this is 0. And then first, let's look at the probability that I just return to 0 this is in 6m minus 2 steps. And then what we do is let's just take a direction, let's say take a E1 step and then take an E1 direction back. So this counts for the 1/6 squared. You can think about this as like a subset of the subset event that what happens here. Right? So any event that is here is definitely implies here. So this is a smaller event. And of course, it's same thing here. Essentially, we just have to single out the last 4 steps for it to return to 0. Yeah, I guess, yeah, the picture, I was thinking of the first return, but it's not first return, yeah. So, yeah, okay, no, yeah. So in the 6m, you can definitely hit 0 in between, but you just have to be at 0 at exactly 6m. Okay, so now with this, the claims that now it just covers all the possible n values, right? Because of these two inequalities. So I'll erase this. So now what we have shown so far is just going to be the following, right? So if we sum it over as n goes from 1 to infinity of p 2n of 0, 0, it's just going to be bounded by some constant c. And when we have summation, n goes from 1 to infinity of this 6 divided by n to the 3/2. And in this case, it will be less than infinity, right? Because for all the other value of these two value of n, it can be bounded by a multiple of the case when n is 3m. So this is the upper bound, and then of course it just reduces into this case, right? And so in this case, then we see that so this is finite. So 0, 0, 0 is transient. Any other questions? Are you guys thinking about the last step? Why over here? Yes. Okay. Oh. Bounded. Well, it will be bounded by the first, and also because of these two inequalities, right? Because okay, maybe I'll just say this. I'll write one more step to justify this. Right? Okay. So imagine over here that so we separated the n into 3 different cases, right? So let's just write this. So let's rewrite the sum into 3 parts. The first sum, let's just say m goes from 1 to infinity. This is p to the 6m, 0 and 0. This is the case when n is 3m. And then plus, okay, I'll just write equal. This is equal to this. We have a summation again, m goes from 1 to infinity. And then this is p of 6m minus 2. In this case here, n is equal to 3m minus 1 of 0, 0. And then plus another sum, m goes from 1 to infinity of p of 6m minus 4 of 0, 0. Right? And in this case, it's just representing all the n is equal to 3m minus 2. Right? So you imagine here we have a summation over all the integer n, and then we separate them into 3 subsets. Right? So you can imagine that we have, this is like integer n, right? We summing over all the integers. Let's say this is, sorry, not all the positive integers. Let's say this is 1, and then 1, 2, 3, and then the first case then essentially is going to be, so these are all the multiple of 3. I'll just write in yellow. So 3, 6, 9, etc. And then there are also oops, I think 1, 2, 3. Sorry, wrong one. Okay, let's erase this one. So this is 1. So this is 3, 6, and 9, etc. And then we can also have the 2, 5, 8, etc., etc. And in the last case, we have these 1, 4, and 7. Right? So we just rewrite this sum as 3 separate sums. They're exactly the same. And here for this term and this term, we can apply the bound on the bound over there. On our left. And that way we get this. So then essentially all the terms that appears here will be just p of 6m. And then we know how to bounce p to the 6m from our first part of the calculation. Okay. Yeah, question.
My question is that final stat.
Yep.
Yeah. Just like argument, like
oh, sure. Well, yeah. So for this one, you can use the integral comparison formula. So ignore the 6. So in general, for the theory, we have the all right on the bottom here. Okay. So this is just this fact. So we have the summation here. N goes from 1 to infinity of 1 over n to the p. So this is equal to positive infinity. If let's say p is between 0 and 1, or 1, and then this is finite if p is strictly larger than 1. And then the way you can think about just look at the integral from 1 to infinity of 1 over x to the p dp as dx, right? And then this is something that we know the antiderivative. The antiderivative of this is just going to be so the antiderivative. So 1 over x to the p antiderivative. This is I think it's 1 over p minus 1, 1 over x to the p minus 1. Wait, p plus 1, p minus 1. Let me think. Yeah, it should be. So it should be minus 1. Minus 1 will be plus. Yeah. Wait, it's a plus 1, right? Is it plus 1 or minus 1? 1 over 1 minus p. Okay, I think. Okay, let's write it this way. This is a good. Okay, it's x to the negative p, and then the antiderivative here is just going to be 1 over over here 1 or negative p plus 1, and then x to the negative p plus 1. Maybe it's easier to write it this way. Yeah. Okay. And then essentially what happens here is that we can see that if p is strictly larger than 1, this x here is still like goes to 0 as we send x to infinity, right? So when we evaluate it, there's no problem. But in this case here, we get into trouble. Of course, here the p is not 1. P is not equal to 1. And when p is 1, it's a log function, right? 1 over p is the log of x. So in that case, the integral here is infinite for this value of p. And then for this particular value of p, this integral is finite. That's all, just an integral comparative test. Okay. I guess we don't have time to prove the Stirling's formula. Okay, I'll think about whether if we want to do the Stirling's formula. I mean, it's a famous formula. You can find like all different sorts of proof online. Maybe I'll just end the class quick with some remarks. Okay. I'll just go to the third board here. It's about the probability of p to the so p to the 2n of 0 and 0, right? So eventually what I've shown is that so this is equal to I think just okay, I'll ignore all the constants. So this is like 1 over square root of n. If the dimension, if in z, and over here we show that this is essentially 1 over n to the 3/2 in if in z3. And can you guys guess what happens in z2? It's just 1 over n, right? If we can take a guess, right? And then if it's 1 over n, clearly it's not summable, right? It's a harmonic series. If we sum as n goes from 1 to infinity of 1 over n, it's still infinite. So in this case, we have the following theorem, right? The symmetric, the simple symmetric random walk, or walk in ZD is recurrent if D is equal to 1 or 2, and is transient if D is greater than or equal to 3. Right, so we'll just end here with this theorem here. Right. So I mean, the main reason here is because you know, if the summation of 1 over n square root of n, this is infinity, and then 1 over summation 1 over n is to infinity, but then summation 1 over n to the 3/2 is finite. Right, we can think about it. Oh, so this is the homework pile. So did everyone pick up the homework? Everyone got a chance to pick up the homework? Oh. I think this is yes, homework. Okay. So any other questions? I think this is so maybe we'll stop here for today. If sure, questions.
So very last, I guess the right here. So we're saying that the last two terms are bounded by essentially the first term. The first term is bounded, the whole thing is bounded.
Exactly. Yes. Okay. Yes.
So in showing the second and third term is bounded by the first term, we're appealing to this, this expression on the left. But where does the 1 to the 6 squared and 1 to the 6 to the 4th translate to this?
Like here?
Yeah, right to the left of that. So this is
oh, the square 6. Oh, it's into the constant c. Yes. Yes. Yeah. So it just like we just bounded by a constant multiple of everything. Yeah. So you can think about this c here is different from the previous c. Maybe I'll write c tilde. So like all the like 1 over 6 to the power are all inside the constant. Yeah, just for the upper bound. Yes. And a question? Yes.
Does this return time is that the similar property holds for higher speeds, so it always acts like
Sorry, does
the return time it always acts like 10 to the negative if you go to the higher dimensions, like if you were to 8, would it act
well,
like
that's a good question. I never really checked, but I would so I don't want to claim anything, but it might be possible. Yes, I never really checked. all the calculation I did was just like, I've seen just 1, 2, and 3. It seems like, yeah. Yes. Let's see. Yeah. Okay. Any other questions for today's lecture? Yeah, sure.
And the probability is 1 over 2. That is.
Yeah. Yeah.
But in this case,
Oh, sure.
The probability is 0.
Right.
It must have the sum is
Sure. Oh, because over here we're looking at symmetric. So it's the symmetric, simple symmetric random walk consider for when in Z corresponds to P is a half. The probability you go to left and right are exactly the same.
Oh, so in this case, no matter what P is equal, well, or not, it must be the recurrent. Is that right?
No, P has to be 1/2. This is what the symmetric means. In Z, symmetric just means the probability that you take a left step and the right step, they're the same. So they just have to be 1/2. And then we did the calculation for Z3. In this case, we take a step with the there are 6 directions, and then we take a step in a uniform probability with 1 over 6. This is just this is what it means like for the simple symmetric random walk, right? So we did consider probability of P when P is not a half, or is that is that your question?
I mean, we know that if P is not equal to
yeah,
the probability if n tends to the infinity, it will not.
Sure, yeah.
That right?
Yes.
And if the n is not go back to the function, and the sum will not be the infinity, it will not be the finite. Is that right?
If P is not 1/2, yeah.
But in this case, it shows that the sum must be the infinity.
Oh, this is because in this case P is a half, right?
This case is about P is up to be 1/2 under the
Sure,
condition
yeah.
that we should get the whole thing.
What do you mean? This is we only consider for
I mean that there is a prerequisite condition that P is 1/2 for the
sure.
turn right and the turn left.
Yes,
Both
yes.
in this case, is that
Yeah,
right?
in all these cases, these are only for simple symmetric random walks.
Okay.
Yeah.
This is
Yeah. So for non-symmetric, they'll just all be transient, no matter what dimension it is. Yeah.
Also, I want to extend a bit more
Yeah.
special problems.
Yeah.
Is that means I noticed that in the three, Z3 and the Z4 and the very high dimension, I think it is very. Is that means it is very complex and many unsolved problems in this case, such as I mentioned the.
I mean, it depends, right? For example, it depends on like what type of problem you look at.
For example, the percolation.
Yeah, sure. Percolation, it's very special. It's like when the dimension is high, one of the major, probably like the biggest open problem, which is the existence of infinite cluster at critical percolation. It's unsolved for it's solved for Z is trivial. There's no percolation. People don't really
Yeah, is that means so many researchers that based on this dimension.
Sure, yeah. So for Z2 is solved, but for Z3 is completely open. And it's also solved for when the dimension D is greater than or equal to 11. But then for the dimension, I think if I
11.
Yeah, it's for D is greater than 11, the problem is solved. So whether if there, so there's no infinite cluster almost surely.
D is equal 3 and this is equal 11. Oh my god.
Yeah. So I mean, it means like this is solved here. Solved when D is equal to 2 and when D is equal to 11. But it's open when D is equal to 3. So,
okay. Thank you very much. Thank you very much.
Yeah. So this is the it depends.
Okay.
Yeah.
Thank you.
Yeah.
Oh, yeah.